Hello everyone. Today we present our project on Bowtie Slot Antenna design using ANSYS HFSS. This project was completed by us, Harshit, Anshu and Kuldeep from Electronics and Communication Department. In this presentation, we will cover the introduction to the Bowtie slot antennas, our design methodology, the design tool, and antenna geometry, comprehensive simulation results, and finally, our conclusions. The Bowtie slot antenna is a wideband planar antenna operating from 1.2 to 3 GHz. Its key features include compact design, good impedance matching, and omnidirectional radiation characteristics. This antenna is widely used in wireless communications, Wi-Fi systems at 2.5 GHz, ultra-wideband applications, and IoT devices. We designed it on FR4 Epoxy substrate with a dielectric constant of 4.4, thickness of 1.575 mm, and a 12 by 12 cm ground plane. Our design procedure consisted of four main parts. First, we launched the HFSS Antenna Toolkit from ANSYS HFSS extensions menu. Second, we selected the Bowtie antenna slot option from antenna library. Third, we configured the design parameters including a center frequency of 2.4 GHz, FR4 substrate material, and a 12 by 12 cm ground plane. The arm dimensions were optimized for wideband operation. Finally, we set up the simulation with radiation boundaries and a frequency sweep from 1.2 to 3 GHz. This is the HFSS Antenna Toolkit interface where we configured our antenna design. The key parameters include inner width of 0.15 cm, outer width of 2.78 cm, arm length of 3.08 cm, and feed offset of 0.71 cm. The center frequency is set to be 2.4 GHz. The toolkit provides a parametric design environment with a predefined antenna templates enabling rapid prototyping and optimization of the Bowtie slot antenna. The three-dimensional view shows the physical structure of our antenna. The brown surface represents the FR4 substrate, while the green areas show the Bowtie slot edged pattern. The symmetric design is compact by 12 by 12 cm, demonstrating the antenna's planar configuration ready for fabrication. This visualization shows the surface current distribution to the antenna with a maximum value of 1.286 into 10 to the power minus 13 volts per meter. The current radiation at the slot edges validates our Bowtie geometry and confirms the radiation mechanism. These edge currents are what that generate the radiated electromagnetic fields. The return loss or S11 parameter shows resonant at 2.5 GHz with the values below minus 13 dB at the minimum. The antenna maintains excellent impedance matching across a wide bandwidth from 2 to 3 GHz. S11 indicates reflected power and values below minus 10 dB ensure efficient power transfer with minimal reflections. VSWR or voltage standing wave ratio quantifies impedance mismatch. Our antenna maintains VSWR below 2 from 2 to 3 GHz with a minimum value of 1.5 at 2.5 GHz. Values below 2 indicate less than 11% power reflection, which is ideal for practical antenna systems. The input impedance plot shows the real part approaching 50 ohms around 2.4 to 2.5 GHz. Our target operating frequency, the smooth impedance variation, demonstrates matching with the standard 50 ohm system impedance for optimal power delivery across the frequency band. This three-dimensional gain pattern visualizes radiation energy distribution in all spatial directions. The antenna achieves a maximum gain of 5.32 dB with nearly omnidirectional radiation characteristics. The pattern shows excellent symmetry, making it suitable for mobile and wireless applications requiring broad coverage. The two-dimensional gain patterns show radiation in the principal E and H planes. The red curve represents phi equals to 0 degrees, while the green curve shows phi equals 90 degrees. Both patterns exhibit a figure 8 shape with a maximum gain of 3 dB. These principal plane cuts shows bidirectional radiation typical of slot antennas. The three-dimensional directivity pattern shows a maximum directivity of 5.54 dB. The concentrated main lobe with low back radiation indicates efficient energy focusing. Directivity shows how well the antenna focuses energy compared to an isotropic radiator, enhancing signal strength in target directions. This plot tracks directivity variation with frequency. The directivity remains stable between 4.9 and 5.5 dB across the entire band from 1.2 to 3 GHz with a peak of 2.7 GHz. These stable values confirm wide band capability with consistent directional characteristics. At the critical Wi-Fi frequency of 2.4 GHz, our antenna maintains a 3 dB gain with bidirectional coverage. The polar representation shows the pattern characteristics with a marker at 120 degrees. This bidirectional coverage is ideal for wireless router and access point applications. The polar plot shows angular gain distribution with a maximum gain of 5.56 dB at broadside. Multiple nulls are visible at the pattern showing excellent symmetry. This visualization helps identify optimal antenna placement for desired coverage and reveals null directions to avoid. The axial ratio plot shows polarization characteristics with a peak of 82 dB around 1.9 GHz. This high axial ratio confirms strong linear polarization with expected for bow-tie slot geometry and suitable for linear polarization applications. Radiation efficiency shows the ratio of the radiated power to the input power. Our antenna achieves near unity efficiency for over 97% across the entire band. This indicates minimal power loss in the antenna structure and FR4 substrate, with efficiency close to 100%, confirming excellent design. In conclusion, we successfully designed and simulated a bow-tie slot antenna with the following specifications: operating bandwidth of 2 to 3 GHz demonstrating wideband coverage, return loss below 13 dB with VSWR below 2 across the entire band, ensuring excellent impedance matching, maximum gain of 5.32 dB and directivity of 5.54 dB, gain of 3 dB especially at 2.4 GHz Wi-Fi frequency, radiation efficiency exceeding 97% with minimal losses and linear polarization characteristics. This antenna is suitable for Wi-Fi and WLAN systems, ultra-wideband applications, and wireless communications. We used ANSYS HFSS 2025 R2 with the Antenna Toolkit for this design. Thank you for your attention. We welcome any questions about the Bowtie Slot Antenna project.